So how's everyone doing today? All right, good to know. Welcome to this session on unlocking real-time predictive insights from your Internet of Things. You know, this is my first time in Atlanta, and I was doing touristy things here over the weekend. One of the things that I did was visit the CNN building and take their tour. Not very long ago, CNN used to have this tagline that went along the lines of, "Be the first to know." That really stuck with me, and I was reminded of that because of its relevance to this talk and big data processing in general. There's this notion that by being the first to know, there's a certain implied advantage that one has. And that is largely the theme of this very talk as well. We're all familiar with big data processing. A lot of the sessions at Ignite, especially the data focus sessions, are all about extracting insights from a large corpus of data. This session is specifically about getting insights really quickly. The whole underlying hypothesis is that if you have an insight, the sooner you have an insight, the sooner you can act on it, and the sooner you can unlock business insights. We're all familiar with the Internet of Things. I have one such thing here with me. It's a small sensor tag, and you might have seen this Power BI dashboard that was showing you the real-time readings from here. Oops. This guy here. So this is showing you real-time readings from the sensor tag. In this session, we're going to go over not just getting readings from one sensor, but hundreds and thousands of sensors. We have partners such as Honeywell that build building monitoring solutions. A building like this could have hundreds and thousands of sensors, sending in humidity information, temperature information, carbon dioxide sensors, and then you can take automated actions in near real time based on the certain values, based on certain criteria that you can code up and the processing logic that you can code up. So let's get started. My name is Sam Chandrasekhar. I'm a program manager on the Azure Stream Analytics team. In this talk, we'll be primarily focusing on hot path IoT analytics that will give you these near real-time insights. We all agree that time to insight is critical, and there's this thing about decision latency. In the old world, the modus of operandi seems to be one where you collect a whole bunch of data, you store it, and then you apply powerful machine learning algorithms and things like that, and ask questions about your data when the data is at rest. With increasing pressures on time to insight, we no longer have that comfort where we can ask questions on our data after it comes to rest. The new world is all about asking questions to your data as it is moving. An analogy that I like to provide is, if I were to ask you the question, how many blue cars are on the roads of Atlanta right now? One potential strategy could be, I'm going to drain out all of the roads into a large yard and then have all of those cars come to rest, and then I'm going to count all of them. That is in many ways representative of batch analytics, where you wait for data to come to rest and then you ask questions about it. Streaming analytics and real-time processing is all about asking questions about your data as it is moving. So the equivalent analogy would be that I would be able to count the cars that are on the streets that are moving as they're moving, as opposed to waiting for them to come to rest in some repository. There's also the realization that some of these insights that you can get are perishable. There's a window of opportunity where these insights are useful for businesses. And if you miss this window, then the insights are no longer as valuable. And that is also a core theme that is built into near real-time stream processing that we're going to talk about in this session. You know, just to clear out some of the terminology here, when we talk about real-time stream processing, folks talk about event stream processing and simple event processing as well as complex event processing. I want to set the stage by saying what you see here is what complex event processing means in the context of this talk. In the case of simple event processing, folks have been doing things like filtering, transforming, and enriching data, simple transformations on single event streams. And then you can do more advanced things by aggregating things, specifying rules, but these have all been in the currency of individual event streams. In complex event processing, we're taking in multiple event streams, correlating them, joining them, asking questions based on data that is flowing across different streams and things like that. So we're going to do complex event processing to unlock predictive insights from your Internet of Things. This doesn't necessarily have to be restricted to your Internet of Things, but IoT is big and hot, and there are lots of possibilities here. When it comes to the scenario possibilities, there are two broad themes. There are scenarios where you can do things for human actors, and then there are scenarios where you can automate things end to end, where a machine is essentially replacing a human actor. In the case of what you can do for a human actor, live visualizations and real-time dashboards, along the lines of what I showed you, can essentially empower humans to take actionable decisions based on some aggregated information or some insights that you show on a dashboard that is updating in near real time. I showed you one such dashboard. I'll show you one more. The whole idea here is that you give someone a command and control console, gives them a view of all aspects of what they're interested in, and then they can take actionable decisions. The extension of that would be one where you replace the human element and you automate things end to end. We have a few examples of that I'll go over in some detail. So the three canonical use cases for Azure Stream Analytics, as well as any hot path stream processing, is really one where you enrich your data to move it elsewhere so that you can ask questions about it when the data is at rest, sort of along the lines of this Lambda architecture. The other scenario is one where you ask questions about your data as it is moving, and then you display it to a human on a real-time dashboard to give them a live visualization so that they can take corresponding actions. And the third scenario is one where you can automate workflows. You can trigger off workflows. You can kick off downstream processes based on certain conditions and triggers that go off. Now I'm going to give you one such example right now. And I'm going to switch back to Power BI. And I'll show you this predictive maintenance demo. So what we're doing here is that we have collected a bunch of information from airplanes. This is publicly available information from NASA and a bunch of other sources. This is historical data, but we're replaying it as if it were happening in real time. And I have a dashboard here that is updating as we speak that is showing the number of alerts for several interesting things in the airplane. What I'm going to do is I'm going to zoom in on a certain airplane engine. So what you see here is that every part of the airplane engine has been carpet bombed with sensors that are streaming in telemetry information. And this is updating in real time, and I can click on each part and it'll give me the number of alerts that each sensor is generating. And so if I was an aircraft maintenance person, I could make sense of this and take actionable decisions. I also have the ability to use a machine learning model under the covers and get actionable recommendations like this, where this chart is giving me, on the evidence of those sensor alerts, the predicted remaining useful life for this specific airplane engine. And this is really powerful because of the kind of business models it can unlock. When we talk about the Internet of Things, it is also causing a big disruption when it comes to business models. In the past, you had device manufacturers selling the device to the end customer. And then subsequent upkeep and support and things like that was largely the responsibility of the customer. You could have contracts in place to do that, but the responsibility of that lied with the customer. We're now witnessing a paradigm shift where the device itself is not being sold as a component, but it's being provided as a service, almost as a subscription service. So in the case of airplane engine, there is plenty of precedent for cases where the airplane engine is now provided to the airline in the form of thrust hours. So the airplane engine manufacturer sells thrust hours to the airlines, and the airlines now get more determinism when it comes to how much they pay, and the headache associated with support, maintenance, upkeep, and all of that is taken away. And this is possible because the device manufacturer the airplane engine manufacturer in this case, has full insight into the field performance of that device. And to do that, they essentially shower their devices with sensors and actuators that are constantly sending out telemetry data to the cloud so that they can get actionable insights and do predictive maintenance on these things so that they can reduce downtime for their customers. A big customer of ours that is using this in production as we speak is the elevator company ThyssenKrupp, that is using Azure Stream Analytics for hot path IoT analytics for the specific purposes of doing predictive as well as preemptive maintenance on their elevators that are in buildings around the world. I remember in this very conference center, one of the elevators was a ThyssenKrupp elevator. That is not the only scenario. There are a plethora of other scenario possibilities for hot path IoT analytics. My favorite ones are around connected car and fleet monitoring scenarios. We have auto manufacturers that are taking advantage of some of our functionality to essentially stream out telemetry information from the car and again alert folks when there's a need to service their car. Or in near real time, if the fuel level is low, and if it is known that there is a nearby gas station, you can send out an alert. Similarly, if there's a storm approaching and you're heading towards the storm, the auto manufacturer or any other intermediary can send out the alert to the driver so that they can make a corresponding change. We also have real-time patient monitoring. It's used extensively in medical devices. One of the companies that's using us here is Aerocrine, which makes these devices that you blow into, and in a remote site, based on certain aspects of one's breath, it can be told if there's a likelihood that one has asthma or not. So to service these devices, they have a bunch of sensors that are sending out data to the cloud to make sense of this, to give them actionable recommendations. Smart grid is another very common use case. Predictive maintenance, IT infrastructure and network monitoring. There are no shortage of possibilities, and I'll be demonstrating some of these scenarios to you and what it will take to realize these things using Azure Stream Analytics and the rest of the Azure stack. If we go look at what an IoT analytics pipeline for the hot path looks like, this is what we have in mind. So to take a step back, when I use terms like hot path, I'm specifically alluding to asking questions about data as it is moving, as it is being generated from the devices. There is also this notion of a cold path, where I not only ask questions about data as it is coming out of sensors and devices, but I also do things like aggregate them in a repository. And then when the data is at rest, I can ask questions about them using batch analytics. So in this specific case, you have applications and devices that are sending in data to event queuing and stream ingestion systems, either directly or through gateways and hubs. And in Azure, we have event hubs and IoT hubs that are essentially low latency message queues to aggregate large numbers of events that your data exhausts are sending in. How many of you all have heard of Apache Kafka, out of curiosity? Good to know. How about event hubs? Good to know. An IoT hub? Fantastic. So they all perform effectively the same kind of functionality, which is to aggregate events as they come in from your applications, from your data exhaust, from your devices. And then you have a stream processing system. This could be Spark streaming on Azure, or Storm on HD Insight on Azure, or Stream Analytics, which is the focus of this talk, which essentially reads off these event queuing systems, event by event, and has a bunch of temporal processing logic where you can ask questions about the data that is coming in. And then you can also take a bunch of downstream actions. You can go in for real-time dashboarding to visualize your data, or you can enrich it and store it in long-term storage for the purposes of batch analytics, or you can trigger off custom workflows based on conditions being met that you get to stipulate. So that is sort of the end-to-end pipeline. And you also have the ability to call out to Azure Machine Learning and services like that. So you can do real-time scoring using machine learning models on events that are streaming in. So there was a question, do we have cognitive API support to call out from Stream Analytics? Not at this time. We have the ability to call out to Azure Machine Learning through what is effectively a function call. I have a demo of that and more details on that later in the presentation. We'll get to that in a little bit. You could ask the question, why Azure Stream Analytics? There are no shortage of stream processing options. There is SAMSA, there is Flink, there is Storm, there is Spark Streaming. You could ask the question, why Stream Analytics? And really, the answer comes down to three key differentiators. The first one being programmer productivity. If you were to take Storm and build out a simple solution where you have a bunch of filtering operations, a bunch of projection operations, and a bunch of time-windowed processing. In this example that we ran, it takes close to about 2,000 lines of Java code to implement that in Storm, or you can replace that with 3 lines of code in Azure Stream Analytics. We have a SQL-like query language with inbuilt temporal semantics, and we'll go over some of the scenarios in detail in subsequent parts of this presentation. But that is sort of the key to our programmer productivity. You can achieve more with less, and we have inbuilt temporal semantics that will allow you to unlock a whole bunch of scenario possibilities without having to roll out a ton of code. The second key differentiator is the integration that we have with other Azure services, with Event Hub, for instance, with IoT Hub, with Power BI, with sinks like Azure Data Lake Storage or Azure Blob Storage or DocumentDB. So if you're going to implement a Stream Analytics solution, using a matter of a few clicks, you can deploy out an end-to-end stream processing pipeline, as opposed to writing a whole bunch of glue code to link one service to the other. The third one sort of combines the best of the first two, which is the fact that it provides you the lowest total cost of ownership as a result of reducing the time, effort, and energy to run and maintain a stream processing pipeline. It's a fully managed Azure service. So if you look at the ingredients of what it would take to stand up a streaming solution, by virtue of this being a fully managed Azure service, you don't have to worry about infrastructure, procurement, and setup, or cluster management, or topology construction, or glue code to speak with sources and sinks, to call out to machine learning. Scalability is seamless. It's taken care of. We also have monitoring and troubleshooting mechanisms to sort of package up all of this into a readily usable service without you having to do extra work. Now, you might ask the question, how does this compare and contrast with, say, Spark Streaming and Storm, which are also available on Azure on top of HD Insight? In the case of HD Insight, what we do is we run the Hortonworks Hadoop distribution as a service. We offer some value adds. We claim we offer an SLA of 99.9% availability, which is also true for Stream Analytics. But when you're dealing with Storm or Spark Streaming, you're dealing with the currency of clusters. It's a fully managed Spark Streaming or a Storm cluster. If you want to scale that, you're going to add a node to that. A node is essentially a virtual machine. In Stream Analytics, you're not dealing with those low-level constructs. You're not going to articulate. You won't have to map out and write out your topology. All of that is taken care for you under the covers, and as a result, the amount of time, effort, and energy it would take to roll out a solution is significantly lower. I was telling you about the SQL constructs and the SQL-like syntax. This is essentially a subset of the functionality that we have. What we have done is we have taken the core parts of T-SQL, and we have enhanced it and extended it with a bunch of additions, especially around temporal semantics, that are most applicable to streaming scenarios. If you look at most streaming scenarios, it is, it is asking questions to data in motion, and it is asking questions with a certain time boundary in mind. Because this is a continuous stream of data, to make sense of it, you'll have to discretize it into specific time boundaries. And we have functionality such as windowing, hopping windows, sliding windows, and tumbling windows that will allow you to do that and ask these questions that you want to on your real-time streams of data without having to roll out a ton of code. This is in the spirit of this being a fully managed Azure service. We also offer an enterprise-grade SLA of 3 nines of availability. Under the covers, we have an automatic checkpointing and a fast restart logic that will guarantee that there is no data loss, even in the event of certain internal failures or job errors and things like that. We also provide a guaranteed event delivery semantics. So we say we will assure you of at least once delivery for your events. And it's also available in 19 Azure regions, including the China and Germany regions, which come with their own unique value adds in terms of privacy and compliance related stipulations. We also are adherent to major global compliance requirements, some of which are here. So when it comes down to the capabilities, if we look at a stream analytics job, it really consists of 3 parts. There's an input, there's a query step where you articulate your processing logic, and there are 1 or more outputs. To sort of go deeper into explaining the capabilities of stream analytics, I'm going to take up a scenario here, which is a toll booth scenario. So let's assume that there's an expressway, a freeway with multiple lanes, and there's a toll booth, 1 for each lane, where that cars are passing through to make a payment to use the services of the roadway. We're going to assume here that there are 2 checkpoints, an entry checkpoint and an exit checkpoint, both with RFID readers that are looking at some interesting information that is usable here from these cars. So this is the example that I'll use to talk about what you can do and how you can use stream analytics. I also here have reference data, which you can think of as a static database that we can look up. So there is this notion of an event stream where you have a bunch of data that is streaming in from these toll booths, and then there is also less frequently changing data. We call that reference data that you can use to look up, you can join against, and things like that. And things like registration information is data that we can, for all practical purposes, think of as seldom changing or static data. So this is not a data stream, but we'll be taking advantage of that as well. So since this is a SQL-like language, I'm going to start with an example of filtering. So I have a bunch of criteria here, and say the task here is from an incoming stream. I want to know what vehicles satisfy these criteria, and display, passenger if it's type 1, commercial type 2, etc. Going back for a second here, if you look at this entry stream table, toll ID essentially alludes to the lane on which the toll booth is present. So if you look at the query itself, this is very SQL-like. This is a common filtering operation. Out of curiosity, how many of you are familiar with SQL? All right, that's literally everyone. So I will not spend too much time into the details of this, because this is a fairly fundamental filtering operation using SQL. There are other parts there around date part and things like that. We'll get into the details of that. The other scenario that I'd like to talk to you about is joining. So you can have multiple streams coming in, and you can essentially join these streams. But as you join these streams, since this is a streaming scenario, you will have to be mindful of the temporal semantics. You'll have to specify a time bounds upon which you'll perform that join. And you notice that there is this clause called date_diff. That is a mandatory clause that you'll have to specify in the stream analytics query language our SQL-like query language, when you say that, all right, I will join these streams upon this condition with the additional condition that I'm looking at it within a certain specific time bound. And that is exactly what I'm articulating with datediff. There's a question right there.
Yeah, so if you ever run into a scenario where you're comparing the two streams and you have null data on the other side, will this show up as null?
So the question is, if you're comparing two streams and if you have no data on one of the sides, will it show up as null? And the answer is, yes, it will. And the scenario for that is this is a fantastic segue to my next slide, is a left outer join, where if you have null data, you can specify that in the where clause and find out that it is null. So a left outer join is super useful for identifying patterns, where you can, in this case, you're detecting the absence of events. Specifically here, I'm asking report all cars that have entered the toll booth but have not exited in the past 5 minutes. So I'm looking for the absence of events, and this is where a left outer join comes in, especially because I can check for that null condition. Now going back to the previous slide, what I'm looking for here is that I'm getting multiple streams, the entry stream and the exit stream, and I'm asking the question, find the time in seconds required for vehicles to pass the toll booth, and display this as well. So if you were to implement this in another framework, it would take a lot of lines of high-level code in Java or Scala or even C#. So here you can ask questions using SQL. It's a declarative language with the temporal semantics. So I'm guessing the join here itself is fairly intuitive. I'm looking for the license plate as the condition of the join from the input stream and the exit stream. Again, just to recap, there are two sensors in this toll booth, one at the entrance, one at the exit. They're both streaming out data. I'm performing a join on the license plate ID that is recognized by each one of these to compute what is the time that the vehicles spend inside the toll booth. For the purposes of performing this join, there is that datediff condition. You'll also notice there's another datediff clause in the select statement itself. And that is essentially subtracting out the absolute times recorded by these two sensors to give me the time that was actually spent within the toll booth. So in lots of IoT scenarios, this is very common. Building monitoring too, where you have multiple sensors and you're looking for differences between things where the sensors are sending in related but different information. Then there's the notion of windowing. Since temporal semantics is so very fundamental to stream analytics and how it functions, a core part of the query language is the concept of windowing. So we have these, there are three kinds of windows. We have sliding windows, hopping windows, and tumbling windows. These are fixed length windows, and there's an output generated at the end of each window. And these are used in the group by clause of your SQL statement. In this case, in the example that you see here in that diagram right there, I'm essentially performing an aggregation, a sum of the values contained in each one of those events and displaying it at the end of a certain time window. So this is a tumbling window where essentially I have a window of a fixed size that is repeating on end. So in this case, I'm asking the question, give me a count of vehicles entering each toll booth over the last 10 seconds, and I want the answer to this question to show up every 10 seconds. And for this, I'm using this tumbling window. Again, I want to highlight the fact that the simplicity of this, in 3 lines of SQL, I can do what would have taken a lot more lines in Java if you were to roll out logic like this from scratch. So the idea again here is I'm using the tumbling window clause along with the group by statement, and I'm also going to specify the span of that window. And count here is the aggregation operation for that specific window. Notice that I'm also getting this for every toll booth. Now, if I want to ask the same question, give me a count of vehicles entering the toll booth over the last 10 seconds, but I want to ask this question at an increased frequency, where I want to ask this question every 5 seconds as opposed to 10 seconds. I have this window called a hopping window. And again, the only change in terms of how you would write your code is that you replace that with a hopping window. A hopping window has 2 parameters as opposed to just one. There is the span of the window, the size of it, and then there is the hop frequency, which is in this case 5 seconds. So you'll notice that there's an overlap, and you have events that are a part of multiple windows at the same time. We also have another window called a sliding window. This is super useful and super interesting for detecting patterns. The whole premise behind the sliding window is when an event occurs, you can look at activity either before or after and try and make sense of it. So in this specific case, I'm trying to ask the question, find all toll booths that have served more than 10 vehicles in the last 20 seconds. And a sliding window generates an output when an event either enters or leaves it. So to be clear, when you kick off a sliding window under the covers, it starts off from the time you kick it off, and then it's slowly incrementing by a small amount, and it's moving forward. And when an event either enters or leaves the system, an output is generated. And this is useful for a whole bunch of pattern recognition scenarios. This is a very simple example that I have there. So before I move forward, are there any questions? Yeah, we have 2 questions here.
So in this scenario,
Mhm.
you have a fixed value for the more than 10 vehicles. Could you make that like a dynamic value as say the average? So if it served more than the average in the last 10 seconds or 20 seconds, would that create the window?
Absolutely. Here I'm using the count function. Instead, I could use a different function. The purpose of this example was primarily to highlight the capabilities of what a sliding window can, but you can use more complex logic to ask questions that are more than just the count of things. There's a question right there, and I'll get to you.
Well, no, just a compliment what he was asking, but in that scenario, couldn't you, instead of saying greater than 10, just do the average of?
Yeah. We'll get to him, and then we'll come back to you. Just to repeat, the question is, if I have out-of-order events or late arriving events, I'm guessing those are the 2 broad categories you're alluding to, what do we do? And the answer to that is we have explicit policies that you can specify to deal with out-of-order as well as late arriving events. I was hoping to cover that later on, but since we've gotten to that, let me talk about that. So you can specify job-level policies to deal with either late arriving events or out-of-order events. And the policies could be along the lines of, if an event is late by a certain threshold amount of time, I can choose either to drop it and discard it, or I can choose to adjust the time of that to a time that is within the window of interest. And I could do the same thing for out-of-order events as well. You can ask under the cover, Stream Analytics uses this buffer that we call the reorder buffer for every time window, where essentially we open out a buffer, if it's like a hopping window, for the length of the hopping window. And then we're waiting for events to arrive. So these events could arrive late, or they could arrive out of order. So what we do typically is that we wait for all the events to arrive, and then we sort that based on time, and then we go ahead and generate the output. Now, we give you fine-grained knobs and controls to change the behavior of that. The specific behaviors of interest are that you can adjust these late arriving events, or you can choose to drop them. Again, these are super useful for scenarios where, like you said, you could have unreliable network transmission, or you can have gateways with a certain fixed amount of delay that you can offset by explicitly articulating that I want to offset it by this many seconds or minutes and things like that. So does that answer your question?
Yes.
Right. we'll get to him and then we'll get back. Yeah. Right. Right. So, fantastic question. So the question was, in some of these examples, I have this clause called timestamp by. So let me spend some time talking about what that is, and then we'll get to the specific example. So typically, by default, what we do is that every event is associated with a timestamp. The timestamp that we look at by default is the enqueue time, the time at which it enters into Event Hub or IoT Hub. And if you do not specify that timestamp by keyword, we will treat the enqueue time of a specific event into Event Hub or IoT Hub as the timestamp that on the evidence of which we will perform downstream processing. Now, you can overload that and you can override that behavior by specifying that I want a custom field that is a part of my data payload to be used for temporal processing. So if I go back a few slides and show you the schema that we were using, yeah. So in this case, the payload itself has a certain time. So which is the time at which the car entered or the car was recognized by this specific sensor. This is more interesting than the time at which this event was enqueued into the Azure Event Hub service. So I can use the timestamp by keyword to use this as the criteria, as opposed to the default behavior, which is to use the enqueue time. And you'll notice that in all of these examples, I have timestamp by, timestamp by. I'm recognizing, let's say here, entry stream, and using the timestamp by entry stream, things like that. So the question is here, why hasn't it been used? So the good catch, this is an error on my part. It should have said timestamp by that specific field. I'll go ahead and fix that. But thank you for that. We got to talk about the timestamp by keyword. There was one more question here. Yeah.
Are you looking at adding more window types, like count window or something like that?
Absolutely. So the question is, are we looking at adding more window types? The answer is absolutely yes. We're looking for scenarios where if we have a certain canonical kinds of windows where you can perform faster processing, or you can it would be more productive for you to write your code using our query language. So the answer is absolutely yes. And if you have suggestions or if you have requirements for different kinds of windows, come talk to us, come talk to me, and we'll try to fit that into our schedule.
Yeah. Okay.
Yep.
One more add-on, because I'm looking for something where time is not obvious before, right? So,
Mm-hmm.
Is there any workaround up to now in order to create something like a count window? I think you had that in Stream Insight, and so that would be
So
the type of thing I'm looking for, right? So say, well, I want that window closed after a certain amount of time, or whenever I hit like 100 or 10 occurrences.
I see what you mean. So you want to close out a window upon the expiry of a certain condition. In many ways, a sliding window can help achieve the same functionality, because an output is generated every time an event enters or leaves the system. And you can have a multi-step query where you can have multiple windows that are sliding across the same data stream. In our documentation, we have a few examples to illustrate how you could use that. So I can point you to that later, or maybe I'm misunderstanding a question. We can chat offline about it. Also, this specific example that I went over, this toll booth scenario, we have all of the code to implement that and to run that in practice on GitHub. I didn't show it to you here because it would take, I was concerned about the timing of it, but all of that code is available on GitHub. We have a self-service walkthrough examples where you can try that out yourself, which includes event generators for the toll booth itself. Next up, I want to talk to you about custom code. If, for whatever reason, the capabilities of this query language that we went over do not suffice your needs. For example, let's say the scenario that he brought up is a legitimate scenario that we do not support. there is the ability to write custom code to bridge that gap. And so far, as a start, we have first started off with JavaScript, but we hope to extend this even further. You have the ability, and this functionality is in private preview at this time, and this is the first place we're announcing it. We have the ability to have user-defined functions in JavaScript. So the canonical use cases are, for string parsing, manipulation, date and time, math operations, array manipulation, where JavaScript provides a bunch of existing functionality that you can readily use through libraries or stuff that you can get from elsewhere. There are a bunch of restrictions in terms of the capabilities at this time. You can't call out to REST endpoints. You can't, pull reference data or from external sources. You can't do custom aggregations at this time yet. But we're open to, and we're thinking about additional languages that we want to support beyond just JavaScript. This represents a first start, and this functionality is in private preview. If any of you all are interested in using this, come talk to me, and I'll have that unlocked for your Azure subscription. In terms of how you'd go about using this, again, you'd use this as effectively a function call in your SQL-like query language. This also comes with a bunch of metadata that you'd have to specify beforehand to the job, which sort of tells the job this is your user-defined function, here are the properties associated with it, and the usage of it, in this case, the hex to int function is something that you'd take advantage of, just like a function call.
You have the ability to break up a long SQL query into parts so you can reuse parts?
So the question is, can you break up a large SQL query into parts? And the answer is absolutely yes. We have this keyword that we call width that allows you to sort of section it out into specific steps, each that contain one logical set of operations to sort of make your code more modular, readable, and reusable. We do not support libraries at this time. It is something that we're thinking of and we're working towards. But right now, you'd have to copy and paste the entire thing. It is a manual step right now, but we hear you, and this is something that we're actively looking at. I want to talk to you about reference data. I've already covered some of this. But the idea here is that in addition to real-time data that is streaming in, we also have the ability to ensure that if you have static data that does not change, you can ensure that that interacts with your real-time streaming data as well. In this case, we have a bunch of reference data that I'm performing a join on. I have an example to substantiate this. So for instance, in the previous scenario that we went over, if I want to report all vehicles that have entered the toll booth with expired licenses, remember there was this table that had registration information that essentially corresponds to reference data. Today, the only source that we support reference data input from is Azure Blob Storage. So you're performing a join on reference data. And for all practical purposes, the way you deal with reference data in your query is close to identical to how you would use it with an event stream. And the restriction on reference data, of course, is that this is not intended for data that is likely to change frequently. The question?
Yeah, so do you have a method in which you can trigger some type of external process to load that data into an Azure Blob?
So the question is, can we have a mechanism to manually trigger the reload of a reference data set, perhaps? Is that correct? And the answer is, at this time, we do not. We have our own frequency for refreshing it under the covers, but this is something that we're actively looking at, and we hope to bring that out soon. So I was talking about scalability earlier. We have this notion of a streaming unit, which essentially translates to the compute footprint of an Azure Stream Analytics job. And it's a function of memory, CPU, the number of storage IOPS, a whole bunch of things sort of encapsulated into this unit that we call a streaming unit. You can add and remove streaming units to your job, and our pricing model is also a function, or streaming units is an input to our pricing model. So pricing for Azure Stream Analytics is a function of two things right now. One is the number of the streaming unit footprint of your job. The second one is the amount of data ingested into Stream Analytics. So the big advantage of streaming units is, unlike, say, Storm or Spark Streaming, you're not dealing with things at the currency of clusters and nodes. So to scale something like that, you'd have to throw a box at it, a VM perhaps, and you'd have to, in some cases, probably rewrite your cluster topology. In this case, you're just adding or removing streaming units to your job, and all of the scaling under the covers is taken care of. So moving forward, I want to talk about partitioning to improve throughput. So Event Hub and even IoT Hub supports this notion of partitions. So to give you an example, let's say there is some sort of a condition because of which, say, trucks go into toll booth 1 and cars go into toll booth 2, and say motorcycles go into toll booth 3. And maybe that's an artificially imposed condition. So what you can do is you can say in Event Hub or IoT Hub that events coming in from toll booth X are mapped on to partition X. Event Hub under the cover supports this notion of partitions. And so you can explicitly articulate out that logic, and then in your Azure Stream Analytics query language, in the query that you write out, you can say, deploy this query using a certain partition ID. So what you have is the same instance of the query running against every partition. So you can parallelize this out, you can fan out, and as a result, in many cases, you can get higher throughput than you would if you were just looking at it as a linear stream. In this specific case, if you look at that query, I'm using the keyword partition by, and I'm using a certain partition ID. And this query comes with the presupposition that there is another relationship between partition ID and toll booth ID that I've specified while programming data ingestion into Event Hub from my toll booths. We spoke about out of order and late arriving events. This is what the UI looks like. So you can tweak that around, and you can choose to either adjust events, or you can drop events that are late arriving or out of order. All right, machine learning integration. We have the ability to call out into Azure Machine Learning, where you can roll out your own machine learning model and operationalize that. The two most common scenarios that I've seen for streaming data, especially IoT data, are anomaly detection and sentiment analytics. You can have any machine learning model you want that is operationalized using Azure Machine Learning. This could be, if you already have a bunch of R code or Python code, you could just drop that there and operationalize that. Or you could construct it from scratch using the Azure Machine Learning Studio. I'm going to switch over to a demo where I'll show you some of this in action. So this is going to be a sentiment analytics demo. So what I have here is an app to pull data from Twitter. So I'm going to request you to give me a hashtag to look for. We'll have to pick a hashtag that presumably has plenty of action going around, because we'll want to ingest tweets and look at the sentiment associated with that. MS Ignite. All right. All right, it's fetching tweets. What this is doing under the covers is that it's fetching tweets and it's pushing it to Event Hub. All right, looks like tweets are coming in. So what I have here is a Power BI dashboard where I'm going to show you a visualization of the sentiments associated with this incoming data stream. So under the covers, what's happening is that I'm running, whoops, excuse me for a second. All right, well, that loads up again. So the query that I'm running under the covers for this job is what you see here. And sentiment essentially is a function call that maps onto a specific Azure machine learning endpoint. And there's a sentiment analytics model under the covers there, and we're performing real-time scoring on the data that is flowing in. So this is the dashboard. This is the data that is streaming in. And this is a distribution of the sentiments that's getting updated in real time. Unfortunately, the negative triangle seems to be the biggest one here, but you get the idea of what's going on here. So hopefully you can all get on Twitter and change that to positive. But that's the idea. I also want to announce here that we have geospatial capabilities in Stream Analytics. This is again in private preview at this time. If you want to get onboarded to that, come talk to me and we can unlock that for your subscription. So these are some fundamental primitives that we provide, but more importantly, I want to go over some examples. We have lots of scenarios that have gotten unlocked as a result of having geospatial capabilities in Stream Analytics. Primarily, these scenarios are around geofencing and connected car scenarios. So as you can see there, you can generate events when a certain artifact leaves a certain geofence. So we have customers that have already operationalized this in either pre-production or in some cases even production, where a device, let's say a CNC lathe, refuses to operate if it is taken out of a certain geofence. So you can draw a polygon and mark that out as a geofence for a specific factory. And if you move this device outside of that geofence, it fails an attestation check because of an event that gets generated, and it refuses to function. Things like that. It can also be used for security monitoring. Let's say a large source of the data that we're getting in real time today is GPS data. So if I had a GPS tracker on me, either through my phone, and if I am in some place that I'm not supposed to be and someone is privy to that, they can alarm and alert security. We also have connected car scenarios where if the car is running out of gas, and if a gas station has a promotion or has a fuel price that is lower than the rest of the area, you can alert the driver to that. Or if a storm is approaching, there are no shortage of possibilities here with geospatial capabilities. And the biggest opportunities that we're seeing here is in the fleet management and the asset tracking business, where you have large numbers of artifacts that are deployed around the world, and you want to look at them and visualize them and have automated rules to program against certain conditions. So what I'm going to show you is a demo of this functionality. So I'm going to kill this Twitter feed first. And I'm going to set up another event generator for geospatial data. So what we have done is we have captured a bunch of GPS data from a bunch of trucks, and we're replaying it as if it were happening in real time. And this data is being sent to Event Hub. In addition, I'm also fetching a bunch of weather data and traffic data, and on a Bing map, we're going to overlay this and ask questions about this data that is streaming in real time. So Power BI has support for Bing Maps, but in this specific demo, I'm showing you this visualization outside of Power BI, and this is just a Bing Maps instance that is loading up. Now, I have my, oops. So what I'm going to do is I'm going to say, a bunch of data is streaming in. I'm going to say, display all of the vehicles that I'm tracking on this map. And just to be sure that this is sending data, I'm going to check on this. All right, so the idea here is that I'm getting the location information for a bunch of trucks, and I can ask questions about this data that is streaming in real time. So I have a bunch of toggles on this control here. Under the covers, what each toggle is doing is that it's invoking a query. So what I've done is I've set up using the polygon function, I've drawn a polygon around the state of Colorado. I chose Colorado because, as you can see, the boundaries are fairly easy to sort of write as a polygon. There is no jagged borders. So I have a bunch of data coming in. So I'm going to say, show me all the trucks that are currently within this geofence that is shown by Colorado. And I see truck 11 there. So if I zoom in sufficiently, you'll notice that is actually moving. See, it just moved by half a block. See, it's moving. So similarly, I can say I'm going to invoke a weather layer. So that is going to lazy load a bunch of weather information, and I'm going to paint this map with colors. And the shade of pink or red is going to be representative of the actual temperature there, the average temperature for that specific polygon that I've drawn around each state. So this is loading up in a lazy manner. The first time in this demo, it takes a while to load up, and then once everything's loaded up, it works quickly. So what I can also do is I can say, show me all the trucks that are in my fleet around the US. So as you can see, all of these trucks are showing up, and I have a live visualization of these. If I zoom in into each one of them, I'll notice that they're actually moving as we speak. So this is data that is streaming in real time, and I'm able to ask questions to this data using Azure Stream Analytics queries that I'm able to invoke from these toggle switches. I can also ask a question like, show me all trucks that are in states where the temperature is lower than a certain threshold. Pardon my usage of unit here for temperature. Oops. So we'll give it a while, or why don't we see trucks in places that are warmer. Right, looks like that's taking a little while to load, but yeah, I apologize for that, but I hope you get the idea here, that you're able to ask questions about data that is streaming in, visualize that on a map, draw out geofences, identify points, identify polygons, and run queries under the covers to ask questions there. Looks like one finally showed up. I'm saying, show me all trucks in places where the temperature is beyond a certain threshold. Showed up somewhere in the Northeast. And similarly, in this demo, I can get weather and incidents and traffic and a whole bunch of things. Under the covers, I'm performing joins on both the GPS coordinates, its relative location to geofences, as well as weather data that is coming in. So that is geospatial functions in stream analytics. Next up, I want to talk to you all about monitoring and troubleshooting. Again, we've been hearing a lot of customer feedback that monitoring and troubleshooting stream analytics jobs, because it's a fully managed service, is harder than what folks would like. So again, I'm announcing that we have this capability to have a job diagram with metrics, and I'll show you a demo of that. So far, what we've had is job level metrics. So the amount of input your job is seeing, the amount of output, if there are any data conversion errors, a metric to track that, your streaming unit utilization, how that is trending. You can also have the ability to alert on metrics, so you can have an email sent out or an automated workflow kicked off based on a certain metric hitting a certain threshold. So what I'm going to show you is new functionality that we have in private preview. So I'm going to switch back to my web browser, and I have a stream analytics job here. So I'm going to click on overview. This is the job I have, where I have one input, two outputs, and a fairly simple query. Whoops. Thank you for that. So this is a stream analytics job that I'm looking at in the Azure portal. What you see on the screen is the query itself. It's fairly simple. I have one input and a couple of outputs. So what I'm going to do is I'm going to say, show me the job diagram. This will visualize the steps associated with the query into blocks here. It'll also give me color codes that'll show me the health of the connection to a specific input or output. What I can also do is I can click on this and expand out the underlying partitions to almost give a sense of semantic zoom, where I can drill down into specific aspects and examine their health and see how things are going. So I have event hub with multiple partitions. What I'm doing is I'm breaking that event hub out into individual partitions, and clicking on this will give me metrics information for each of those partitions. In this case, I'm not funneling data into this, but if I was, you'd be noticing that the input events are so many, the output events are so many, and I can do this for intermediate query steps as well. This step has just one underlying step, so it wouldn't break out to anything large, but you get the idea. And as a result of this, you can not only monitor all aspects of your streaming pipeline, but you can also localize issues. If you're having problems, if you're pushing out in a bunch of inputs and not seeing outputs, you can go ahead and localize the source of the problem to a specific step. What you can also do here is you can say properties by clicking on that ellipsis, and it'll show out the corresponding code for just that specific section. This is super useful for isolating out problems. The common theme that folks use is they look for steps that are seeing inputs but not seeing outputs. And then you're able to work backwards or forwards and localize out issues to a specific step, and then you can invest troubleshooting efforts towards that specific step. So this is the new job monitoring and troubleshooting solution that we have. Again, this is in private preview. If you want access to that, come talk to me, and I'm happy to unlock that for your subscriptions. This will all go out public very soon. When it comes to interacting with stream analytics, there are multiple modalities. There's the Azure portal, the old portal, the new portal. You can use PowerShell, .NET SDKs, REST APIs for programmatic access, etc. We're also thinking of new modalities, so if you have any requests, come talk to me, and we can see how that can be done. We have a bunch of customer stories. Lots of folks are using stream analytics in production as we speak. I won't spend too much time here, but we have Honeywell that is doing building monitoring. and building building monitoring solutions for stream analytics. Aerocrine is a medical device company. They sell this device that you blow into which, and based on certain attributes of your breath, like I mentioned earlier, it'll detect if you have asthma or not. So they're using stream analytics for monitoring the sensors inside that device so that it can be accurately calibrated so that the readings are accurate. We have ThyssenKrupp that's doing predictive maintenance on elevators, and we have Fujitsu that is using stream analytics for a very interesting scenario. What they're doing is they have these temperature and humidity controlled rooms that they're using to grow lettuce in. And they want the potassium levels in lettuce to be within a certain narrow boundary so that folks who have kidney disease can consume that, because apparently I'm told that the special kind of lettuce is the recommended diet for folks with a special medical condition. So to ensure that these conditions for growing this lettuce are maintained, they have a bunch of sensors and actuators, all using stream analytics. So the sensors are streaming in data to the cloud. We're making sense of it. There's an anomaly detection scheme. If things go past a certain threshold, then we go ahead and we move the knobs on the thermostats and things like that. So this is all being used in production as we speak. Finally, I have a call to action. What apps could you develop if you could predict, detect, and adapt to live data instantaneously? So there's this notion of the power of now. You don't have to wait for a large duration before you can take actions on the data that you have. You can take advantage of it and in near real time generate outputs. And that is the promise of stream analytics and hot path IoT analytics with the Azure IoT suite and the Cortana Intelligence suite. So those were the topics that I had in mind. If you have any questions or if you want me to deep dive into specific aspects, I'm happy to do so. We have some time left. Yeah.
So do you have any concept within stream analytics of doing like select into either other event hubs or the DocDB?
So the question is, do we have the notion of select into? And the answer is, not right now, but that's something that we're looking at. So come talk to me, and I'll tell you a little more about. I'll give you a more nuanced answer about the possibilities there. Yeah.
So I seem to remember I can put stuff in service bus queues as an output.
Mm-hmm.
And is there any way to call like Azure functions and make a call to a service from data to when a query recognizes something, I can call a function?
Absolutely. So you can output to an Azure service bus queue or topic, and then you can kick off a web worker role to perform custom functions. Or if the other functionality that we have in private preview, and we blogged about that recently, is the ability to kick off Azure function workflows based on certain conditions. So you can have custom code running downstream in your pipeline, and you can do interesting things there. Any other questions, comments? Yeah.
Yeah, could you talk about more, if you do some of these like select type statements,
Mhm.
Windows, is it like a request reply, or is it pub sub, or how is that continually providing data and doing action?
Absolutely. So if you look at the stream analytics pipeline itself, there's a message queue. It could be Event Hub, it could be IoT Hub, or it could even be blob storage. So stream analytics has a cursor that we call an anchor under the covers that is referencing things and then picking off things one after the other in a temporal manner. So by default, we use the enqueue time, but for the purposes of processing using the timestamp by keyword, you can perform temporal operations based on a certain value that is inside the payload itself. But under the covers, what's happening is stream analytics sits in front of a message queue, Event Hub or IoT Hub, and then we're reading off data off of those things. So if you don't have any data in your Event Hub or IoT Hub, there will be nothing to process.
How does my application work with that data? I guess I missed that.
So the whole premise is, if you have a data exhaust, you point that data exhaust to a message queue. Event Hub or IoT Hub or blob storage will do as well. And then you have stream analytics hooked on to the other end of your Event Hub or IoT Hub, and you can perform your processing. You can call out to machine learning. You can You can write to a service bus queue and kick off custom code, or write to a Power BI dashboard, etc. Yep. Any other questions, comments, any other areas we want to get into? We have, I think, 4 or 5 more minutes left. All right, thank you so much, folks, for coming.